Hello there, and welcome to the Deep Sleep Nature channel. Tonight we're descending into a world that exists in perpetual twilight, a realm so distant from our own that it might as well be another planet entirely. The deep ocean. Here, in the crushing darkness miles beneath the surface, life has found ways to flourish that challenge everything we thought we knew about survival. We'll drift gently through layers of water where sunlight has never touched, where creatures paint the darkness with their own living light, and where the pressure could crush a human body in an instant. Yet in this seemingly hostile world, entire ecosystems thrive in ways more beautiful and mysterious than anything we see on land. We'll discover animals that create their own stars in the abyss, volcanic vents that birth oases of life in the deepest trenches, and adaptations so extraordinary they seem borrowed from science fiction. Some of what you'll learn tonight might shift how you see our planet's hidden depths. Some of it may linger in your thoughts, like bioluminescent trails in dark water. And if these gentle explorations into Earth's most remote wilderness help you find peace at the end of your day, consider liking and subscribing, or sharing your thoughts in the comments below. It helps other curious souls discover these quiet journeys into wonder, one sleepy explorer at a time. Now, if you're ready, let's begin our descent into the deep. The ocean's twilight zone begins where sunlight starts to fade. At around 200 meters beneath the surface, we enter what scientists call the mesopelagic zone, the ocean's twilight realm. Here, the last traces of sunlight filter down in pale blue rays that grow dimmer with every meter of descent. This is where the ocean begins to transform from the familiar blue world we know into something altogether more alien and mysterious. In this perpetual dusk, temperatures drop steadily toward freezing, and the pressure increases with every passing fathom. Yet this twilight zone teems with life in ways that would astonish anyone peering down from the surface. Schools of lanternfish drift through the gloom like living constellations, their bodies adorned with rows of light-producing organs called photophores. These tiny lights blink and pulse in patterns unique to each species, creating a silent language of illumination in the eternal night. The creatures here have evolved remarkable adaptations to life in perpetual twilight. Many have developed enormous eyes, sometimes taking up half their skull, designed to capture even the faintest traces of light filtering down from above, or the subtle bioluminescent signals of their neighbors. Others have abandoned sight entirely, relying instead on heightened senses of touch, taste, and vibration to navigate their dark world. As we descend deeper, past the twilight zone, and into the bathypelagic realm, we enter true darkness. Here, over 1,000 meters down, the water temperature hovers just above freezing, and the pressure reaches crushing intensities that would implode any surface-dwelling creature in milliseconds. This is the midnight zone, where no trace of sunlight has ever penetrated, and where life depends entirely on its own ability to create light. The darkness here is not empty. It pulses and flickers with the most extraordinary light show on Earth. Creatures have transformed their bodies into living artwork, adorning themselves with patterns of bioluminescence that serve purposes both practical and beautiful. Some use their lights as lures, dangling glowing appendages to attract prey in the darkness. Others flash brilliant displays to startle predators or communicate with potential mates across the vast emptiness. The chemistry behind this living light is elegantly simple yet profoundly mysterious. Most bioluminescent creatures produce their glow through a reaction between a molecule called luciferin and an enzyme called luciferase. When these two substances combine in the presence of oxygen, they create light without heat, a cold illumination more efficient than any human technology. The colors range from deep blues and greens to rare reds and yellows, each hue serving specific purposes in the creature's survival strategy. One of the most mesmerizing inhabitants of this realm is the deep-sea anglerfish. The female of the species carries a modified spine that extends from her head like a fishing rod, tipped with a glowing lure filled with bioluminescent bacteria. She dangles this living beacon in the darkness, waiting patiently for smaller fish to investigate what appears to be an easy meal. When prey ventures close enough, her massive jaws snap shut with lightning speed, securing dinner in a world where food is desperately scarce. The male anglerfish lives a very different existence. Much smaller than the female, he spends his brief life searching the vast darkness for a mate. When he finds a female, he bites into her skin, and his tissues gradually fuse with hers, becoming a permanent appendage that provides sperm whenever she needs to reproduce. This bizarre adaptation ensures that in the enormous emptiness of the deep ocean, these creatures never miss an opportunity to continue their species. Swimming through these depths are creatures that seem designed by imagination rather than evolution. The vampire squid, despite its ominous name, feeds not on blood, but on marine snow, the constant gentle rainfall of organic debris that drifts down from the surface waters. When threatened, it can turn itself inside out, displaying rows of defensive spines, while its bioluminescent photophores create a dazzling display of blue light designed to confuse predators. Jellyfish in these depths have evolved into forms of otherworldly beauty. The deep sea crown jelly resembles a living chandelier, its transparent bell adorned with cascading curtains of bioluminescent tissue. When disturbed, it produces waves of light that ripple across its body like aurora dancing across a liquid sky. These displays serve to startle predators, giving the jelly precious seconds to escape into the protective darkness. The pressure at these depths is almost incomprehensible. At 3,000 meters down, the weight of water above creates pressure over 300 times greater than what we experience at sea level. This crushing force would instantly collapse any air-filled space, yet the creatures here have evolved remarkable adaptations to thrive under such conditions. Their bodies contain no air spaces that could be compressed, and their proteins and cellular structures have evolved to function normally under extreme pressure. Some deep-sea creatures take advantage of this pressure in unexpected ways. Certain species of deep-sea fish have swim bladders filled with oil instead of gas, allowing them to maintain neutral buoyancy without the risk of compression. Others have developed flexible bodies that can withstand enormous pressure changes, enabling them to migrate vertically through the water column in search of food or mates. As we descend even deeper, past 4,000 meters, we enter the abyss-opelagic zone, the true abyss. Here, in temperatures barely above freezing and under pressures that would crush a surface submarine, life continues to find extraordinary ways to flourish. The creatures of the abyss have evolved into forms so strange they challenge our understanding of what life can become. The deep-sea cucumber, a relative of sea stars and sea urchins, has transformed itself into something resembling a living sock, crawling slowly across the seafloor and feeding on organic particles in the sediment. Some species have developed the ability to swim, undulating through the water column like underwater ghosts, their translucent bodies barely visible against the absolute darkness. Among the most remarkable adaptations in the abyss is the ability of some creatures to withstand dramatic changes in pressure and temperature. The deep-sea snailfish has been found living at depths exceeding 8,000 meters in ocean trenches, making it one of the deepest living vertebrates known to science. Its body is composed largely of water and specialized proteins that remain stable under crushing pressure, allowing it to thrive in conditions that would destroy most other forms of life. The scarcity of food in the abyss has led to some of the most extreme feeding adaptations in the natural world. Many deep-sea predators have evolved enormous mouths and expandable stomachs, allowing them to consume prey much larger than themselves. The gulper eel can unhinge its massive jaws to swallow fish larger than its own body, while the deep-sea hatchetfish has developed a mouth that opens vertically, creating a perfect trap for unsuspecting prey swimming above. In this realm of eternal night, creatures have also evolved remarkable strategies for energy conservation. Many deep-sea animals have extremely slow metabolisms, allowing them to survive for months or even years between meals. Their movements are deliberate and economical, every action carefully calculated to conserve precious energy in an environment where the next meal might be months away. The deep ocean currents that flow through these depths carry more than just water. They transport nutrients, oxygen, and even living creatures across vast distances, creating highways of life that connect the remotest parts of our planet's abyss. These currents help sustain deep-sea ecosystems by distributing the organic matter that falls from surface waters, ensuring that even the deepest trenches receive some nourishment from the world above. As we continue our descent toward the ocean floor, we approach regions where the Earth itself shapes life in the most dramatic ways possible. Here, in the deepest parts of our planet's seas, volcanic activity creates oases of warmth and chemical energy that support some of the most extraordinary ecosystems on Earth. These are places where life has learned to harness the planet's own geological power, creating communities that exist entirely independent of sunlight and photosynthesis, oosynthesis. The first hints of these geological oases appear as subtle changes in water temperature, barely detectable warmth rising through the crushing cold of the abyss. As we approach the ocean floor, the seafloor spreads before us like an alien landscape of rolling hills and deep valleys, covered in a fine sediment that has been accumulating for millions of years. This sediment, composed of marine snow and the remains of countless microscopic organisms, forms a soft carpet that extends as far as the eye could see, if eyes could see anything in this absolute darkness. But then, rising from this seemingly barren plain, we encounter something extraordinary. Towering chimneys of rock pierce the seafloor, belching superheated water into the frigid depths. These are hydrothermal vents, underwater geysers, where the Earth's molten interior meets the ocean's deepest waters. The water streaming from these vents can reach temperatures exceeding 400 degrees Celsius, hot enough to melt lead, yet it doesn't boil due to the immense pressure of the deep sea. Around these vents, life explodes in abundance that seems impossible in such a hostile environment. Giant tube worms, some reaching lengths of over 2 meters, cluster around the vent openings like underwater trees in a fantastic forest. These remarkable creatures have no mouth, no stomach, no digestive system as we understand it. Instead, they harbor billions of specialized bacteria within their tissues. Bacteria that can convert the toxic chemicals pouring from the vents into food through a process called chemosynthesis. This is life powered not by sunlight, but by the Earth's own chemical energy. The bacteria living within these tube worms consume hydrogen sulfide, a compound so toxic it would kill most surface creatures instantly, and transform it into organic molecules that nourish their hosts. In return, the tube worms provide their bacterial partners with a safe home and a steady supply of chemicals from the vent waters. It's a partnership so intimate that neither organism can survive without the other. Swimming through these vent gardens are creatures found nowhere else on Earth. Ghostly white crabs scuttle across the rocks, their bodies so adapted to life around the vents that they cannot survive in normal seawater. Their eyes have either completely disappeared or grown enormous, depending on whether they live in the complete darkness away from the vents or near the faint glow that some vents produce. Some of these crabs have evolved special hairs on their legs that can detect the chemical gradients around the vents, helping them navigate between life-giving warmth and lethal heat. The Pompeii worm has perhaps evolved the most extreme adaptation to vent life. This remarkable creature can survive in water hot enough to kill almost any other complex organism. Its back end lives in water that reaches temperatures of 80 degrees Celsius, while its head remains in cooler water around 20 degrees. The worm achieves this incredible feat through a coating of bacteria that acts like a heat shield, protecting its tissues from the scalding water while simultaneously helping to process the chemicals it needs to survive. Even more extraordinary are the vent shrimp, translucent creatures that swarm around the hottest parts of the vents in numbers that can reach millions of individuals. These shrimp have evolved a unique organ on their backs that can detect infrared radiation, essentially allowing them to see heat. This remarkable adaptation helps them navigate the dangerous thermal gradients around the vents, staying close enough to feed on the bacterial mats, but far enough away to avoid being cooked alive. The discovery of these hydrothermal vent ecosystems revolutionized our understanding of life on Earth. For the first time, scientists found complex ecosystems that existed completely independent of photosynthesis and solar energy. These communities survive entirely on chemosynthesis, the process by which bacteria convert chemical energy into biological energy. This discovery has profound implications for our search for life elsewhere in the universe, suggesting that life might exist in the subsurface oceans of distant moons or on planets far from any star. Between the active vents, the seafloor is not the empty desert it first appears to be. Careful observation reveals a landscape teeming with subtle life. Sea pigs, relatives of sea cucumbers, roam across the sediment in herds, processing the organic matter that rains down from above. These strange creatures move in coordinated groups, following chemical trails in the sediment that lead them to the richest feeding grounds. The deep sea is also home to some of the most patient hunters in the natural world. The tripod fish has evolved 3 elongated fin rays that it uses like stilts, allowing it to stand motionless on the seafloor for hours at a time, waiting for prey to drift within striking distance. Its eyes have adapted to detect the slightest movement in the water column above, and when a potential meal appears, it can strike with lightning speed despite its normally sedentary lifestyle. In the sediment itself, countless microscopic organisms create their own tiny ecosystems. Bacteria and archaea, some of the most ancient forms of life on Earth, thrive in conditions that would sterilize most environments. Some of these microorganisms can survive at temperatures that would denature the proteins of surface life, while others can metabolize compounds that are toxic to virtually every other form of life. The bioluminescence that characterizes so much deep-sea life reaches its most spectacular expressions in the deepest waters. The Atolla jellyfish has evolved one of the most dramatic defensive displays in the ocean. When attacked, it creates a spinning circle of light around its body, a bioluminescent burglar alarm that can be seen from great distances in the clear deep water. This circle of light, scientists believe, is designed to attract larger predators that might eat whatever is attacking the jellyfish, essentially calling for help through living light. Some of the most mysterious bioluminescent displays occur during what scientists call the deep scattering layer phenomenon. Every night, countless small organisms migrate from the deep ocean toward the surface to feed, then return to the depths before dawn. During these migrations, the water column fills with so much bioluminescence that early sonar operators thought they had discovered a false seafloor that moved up and down with the daily cycle. The chemistry of deep-sea bioluminescence has evolved to be remarkably efficient. Many deep-sea creatures can control their light production with precision, dimming or brightening their displays as needed to conserve energy. Some species have evolved multiple types of photophores, each producing different colors or intensities of light for different purposes. A single deep-sea squid might have dozens of different types of light-producing organs, each serving a specific function in its survival strategy. The pressure effects on bioluminescence create some fascinating phenomena. The intense pressure of the deep sea actually enhances the efficiency of many bioluminescent reactions, allowing creatures to produce brighter light with less energy than would be possible at surface pressures. This pressure enhancement may be one reason why bioluminescence is so much more common and diverse in the deep ocean than in shallow waters. As we explore these deepest reaches, we encounter creatures whose very existence challenges our understanding of the limits of life. The Hadal Zone, the deepest part of the ocean found in oceanic trenches, extends from 6,000 meters down to the deepest point on Earth. Here, in trenches like the Mariana Trench, the pressure reaches over 1,000 times greater than at sea level, yet life continues to adapt and thrive. The creatures of the Hadal Zone have evolved cellular mechanisms that are almost incomprehensible to surface dwellers. Their proteins remain stable and functional under pressures that would denature the proteins of shallow water organisms. Some have evolved pressure-adapted enzymes that actually require high pressure to function properly, becoming inactive if brought to lower pressures. In the deepest trenches, we find amphipods, small shrimp-like creatures that have adapted to pressures exceeding 1,100 times atmospheric pressure. These remarkable animals can survive pressure changes that would be instantly fatal to surface creatures, and their cellular machinery has evolved to harness the extreme conditions of their environment rather than merely survive them. The feeding strategies in these deepest waters have evolved to take advantage of every possible source of nutrition. Some creatures have developed the ability to digest wood and other plant materials that occasionally sink to these depths, while others have specialized in consuming the bodies of large animals like whales that occasionally reach the seafloor. These whalefalls create temporary oases of abundance in the food, poor deep sea, supporting specialized communities of organisms found nowhere else. The whalefall phenomenon represents one of the ocean's most extraordinary cycles of life and death. When a great whale dies and sinks to the abyssal depths, its massive body becomes an island of abundance in the nutrient-poor deep sea. A single whale carcass can sustain unique communities of organisms for decades, progressing through distinct stages of decomposition that each support different assemblages of life. In the first stage, hagfish and sleeper sharks arrive to feed on the soft tissues, their movements creating currents that disperse the whale's scent through the water column. These scavengers can strip a whale skeleton clean within months, but their feeding frenzy is just the beginning of a much longer process. As the easily accessible flesh disappears, specialized bacteria begin breaking down the lipids stored in the whale's bones, creating a chemical environment unlike anywhere else in the deep sea. This bone-eating phase can last for years, during which the whale skeleton becomes colonized by creatures found nowhere else on Earth. Bone-eating worms, called osedacs, literally drill into the whale's bones, their root-like structures penetrating deep into the calcium phosphate matrix. These remarkable worms have no mouth or gut, instead relying on symbiotic bacteria to digest the bone's organic components from within their bodies. The final stage of whalefall succession creates what scientists call a reef stage, where the remaining skeleton provides hard substrate for filter-feeding organisms in an environment where such surfaces are incredibly rare. Tube worms, clams, and other sessile creatures colonize the bones, creating miniature ecosystems that can persist for decades. Some whalefalls have been found to support over 40 species found nowhere else, entire evolutionary lineages that have adapted specifically to this unique deep-sea habitat. Between these occasional bonanzas of whalefalls and hydrothermal vents, the vast majority of the deep seafloor exists in a state of near starvation. The organisms here have evolved patience as a survival strategy, with metabolisms so slow they can survive for months between meals. Many deep-sea creatures grow extremely slowly, but live for extraordinarily long periods, some potentially reaching ages that dwarf the lifespans of surface animals. The glass sponges of the deep sea exemplify this extreme longevity. These delicate-looking creatures, built from intricate frameworks of silica spicules, can live for thousands of years. Some specimens are estimated to be over 10,000 years old, making them among the oldest living animals on Earth. Their growth is so slow that they add new material to their skeletons at rates measured in millimeters per decade, yet they can eventually reach enormous sizes, creating reef-like structures on the deep sea floor. The bioluminescent displays in these depths serve purposes that extend far beyond simple communication or predation. Some deep-sea creatures use light as a form of camouflage, a technique called counter-illumination. They produce light on their undersides that matches the faint downwelling light from above, effectively erasing their silhouette when viewed from below. This living invisibility cloak allows them to hunt or hide in plain sight, their bodies disappearing against the subtle glow of the water column. Other creatures have evolved bioluminescence as a form of burglar alarm. When attacked, they release clouds of glowing particles or secrete luminous fluids, creating confusion and hopefully attracting larger predators that might threaten their attacker. The deep-sea shrimp Acanthophyra produces a glowing vomit when threatened, spewing bioluminescent fluid that can disorient predators and provide precious seconds for escape. The color of bioluminescence in the deep sea is not random, but follows the physics of light transmission in water. Blue light travels farther through seawater than any other color, which is why most deep-sea bioluminescence appears blue or blue-green. However, some creatures have evolved the ability to produce red light, which is invisible to most deep-sea predators and prey. This creates a private communication channel, allowing these animals to signal to their own kind while remaining hidden from others. The deep-sea dragonfish exemplifies this red light strategy. These fearsome predators have evolved both red bioluminescence and the ability to see red light, capabilities that most deep-sea creatures lack. They use their red photophores like invisible searchlights, illuminating prey that cannot see the light that's revealing them. It's like hunting with night vision goggles in a world where no one else can see infrared light. As we venture into the deepest oceanic trenches, we encounter environments so extreme they seem to belong on alien worlds. The pressure in places like the Challenger Deep reaches over 1,100 times atmospheric pressure, equivalent to the weight of 50 jumbo jets pressing down on every square meter of surface. The temperature hovers just above freezing, and the water chemistry includes concentrations of dissolved minerals that would be toxic to surface life. Yet even here, life persists in forms so adapted to these conditions that they cannot survive anywhere else. The deepest living fish ever recorded, a species of snailfish, was found thriving at depths exceeding 8,000 meters. These ghostly creatures have evolved bodies that are more liquid than solid, their tissues composed largely of water and specialized proteins that remain stable under crushing pressure. The microbial communities in these deepest trenches represent some of the most extreme life on our planet. Some bacteria and archaea here can survive pressures that would compress surface organisms to a fraction of their normal volume. These microorganisms have evolved pressure-adapted enzymes and cellular structures that not only tolerate these conditions, but actually require them to function properly. The sediments in deep ocean trenches contain communities of microorganisms that may represent some of the slowest living creatures on Earth. With metabolisms so reduced that they divide perhaps once every 1,000 years, these bacteria exist in a state that challenges our definition of active life. Yet they persist, maintaining their cellular integrity across geological timescales in environments that remain stable for millions of years. The chemistry of the deepest waters creates unique opportunities for life to exploit energy sources unavailable elsewhere. Some bacteria in deep trenches can metabolize compounds squeezed from the Earth's crust by tectonic activity, essentially feeding on the geological processes that create and reshape our planet's surface. These chemosynthetic communities form the base of food webs that exist entirely independent of solar energy. The adaptation to extreme pressure has led to some of the most remarkable biochemical innovations in the natural world. Deep-sea proteins fold differently than their surface counterparts, maintaining their structure and function under pressures that would denature shallow water proteins instantly. Some deep-sea enzymes actually become more efficient under high pressure, turning what seems like a hostile condition into an advantage. The reproductive strategies of deep-sea creatures have evolved to overcome the challenges of finding mates in the vast darkness. Many species have developed extraordinary sensory capabilities, detecting the chemical signatures or bioluminescent displays of potential partners across great distances. Some deep-sea fish can sense the electrical fields generated by other organisms, allowing them to locate prey or mates in absolute darkness. The anglerfish represents perhaps the most extreme adaptation to mate finding in the deep sea. In many species, the tiny males become permanent parasites on the much larger females, their tissues fusing completely with their mates. This bizarre arrangement ensures that reproduction can occur whenever conditions are favorable, without the need to locate a partner in the enormous emptiness of the abyss. Bioluminescent courtship displays in the deep sea rival any terrestrial light show. Some deep-sea squid create elaborate patterns of flashing lights across their bodies, complex communications that may convey information about species identity, reproductive readiness, and individual fitness. These living advertisements pulse through the darkness, each pattern as unique and meaningful as any terrestrial mating display. The seasonal rhythms that govern surface waters penetrate even to the deepest parts of the ocean. The daily migration of countless small organisms creates pulses of food availability that deep-sea creatures have learned to anticipate. Some abyssal animals time their reproductive cycles to these subtle rhythms, ensuring their offspring hatch when food is most likely to be available. The pressure waves generated by surface storms can travel to the deepest trenches, creating subtle current changes that deep-sea organisms can detect. These pressure signatures may serve as seasonal cues for creatures living in environments where traditional markers of time, like temperature and light changes, are absent. Marine snow, the constant gentle rainfall of organic particles from surface waters, varies in intensity with surface productivity. Deep-sea creatures have evolved to detect these variations, some species becoming more active during periods of increased food availability. The timing of reproduction, migration, and other energy-intensive activities often correlates with these subtle changes in the food supply from above. The deep ocean's role in global climate regulation extends far beyond simple heat storage. The vast deep water masses that flow through abyssal plains carry dissolved carbon dioxide away from the atmosphere, storing it in the deep sea for centuries or millennia. The creatures living in these depths play crucial roles in this carbon cycle, their feeding and excretion helping to process and distribute organic carbon throughout the deep ocean. Deep-sea sediments act as archives of Earth's climate history, preserving in their layers evidence of past climate changes and ecosystem shifts. The organisms that live within these sediments help process and preserve this geological record. Their activities influencing how environmental signals are recorded and maintained over geological time. The abyssal waters themselves move in vast, slow currents that transport heat, nutrients, and dissolved gases around the globe. These deep currents, driven by differences in temperature and salinity, take centuries to complete their circuits, but play fundamental roles in regulating Earth's climate. The organisms living in these moving water masses travel with them, creating connections between deep-sea communities separated by thousands of kilometers. Human activities are beginning to reach even into these most remote parts of our planet. Deep-sea mining threatens to disturb seafloor communities that have remained unchanged for millions of years, while pollution in the form of microplastics and persistent chemicals has been detected in even the deepest ocean trenches. The creatures of the abyss, so perfectly adapted to their stable environments, may be particularly vulnerable to the rapid changes that human activities can bring. Climate change is altering the chemistry and temperature of deep waters in ways that could profoundly impact these ancient ecosystems. Ocean acidification, caused by increased carbon dioxide absorption, affects the ability of deep-sea organisms to build shells and skeletons. Changes in surface productivity alter the amount of food reaching the deep sea, potentially disrupting food webs that have remained stable for millennia. Yet the deep ocean also represents our planet's greatest reservoir of undiscovered life. Scientists estimate that hundreds of thousands of deep-sea species remain unknown to science, their existence hidden in the vast unexplored reaches of the abyss. Each expedition to these remote waters reveals new species, new adaptations, and new insights into the incredible creativity of life under extreme conditions. The biotechnology potential of deep-sea organisms is only beginning to be understood. Enzymes that function under extreme pressure and temperature, bioluminescent systems more efficient than any human technology, and biochemical pathways that can process toxic compounds all represent potential applications that could benefit human society, while highlighting the intrinsic value of these remarkable ecosystems. As we drift through these deepest waters, surrounded by the gentle pulse of bioluminescent life and the ancient rhythms of geological time, we begin to understand that the deep ocean is not separate from our world, but intimately connected to it. The carbon we breathe, the climate we experience, and the evolutionary history that shaped all life on Earth are all influenced by the processes occurring in these remote depths. The creatures we encounter in our journey through the abyss remind us that life's ability to adapt and thrive knows no boundaries. From the crushing pressures of the deepest trenches to the scalding waters of hydrothermal vents, life has found ways not just to survive, but to flourish in conditions that would seem impossible to surface dwellers. The profound silence of the deep ocean is broken only by the subtle movements of creatures perfectly adapted to their liquid world. Here, where sound travels differently through the dense water, many animals have evolved beyond the need for vocal communication, instead relying on visual displays of living light that pulse through the darkness, like messages written in an ancient, universal language. The siphonophores that drift through these depths represent some of the most elegant examples of bioluminescent artistry. These colonial organisms, related to jellyfish, can stretch for dozens of meters through the water column, their bodies adorned with thousands of individual light-producing units. Each photophore can be controlled independently, allowing these creatures to create waves of illumination that ripple along their entire length. When threatened, a siphonophore can produce a spectacular display of coordinated flashing that travels from one end of its body to the other, creating what appears to be a living constellation moving through the abyss. The deep-sea comb jellies have evolved perhaps the most mesmerizing form of bioluminescence in the ocean. Unlike the chemical light production of most deep-sea creatures, comb jellies create their displays through the refraction and scattering of existing light by specialized structures called setanes. These microscopic combs beat in coordinated waves along the creature's body, creating rainbow patterns that shift and flow like aurora dancing through the water. When bioluminescent particles in the water interact with these refractive displays, the result is a light show of extraordinary complexity and beauty. The pressure at these depths creates effects that seem to defy physics. Water itself becomes noticeably denser, and the behavior of gases dissolved within it changes dramatically. The swim bladders that help surface fish maintain buoyancy would collapse instantly at these pressures. Yet deep-sea fish have evolved remarkable alternatives. Some species produce oils with specific densities that provide neutral buoyancy without the risk of compression, while others have developed tissues with unusual water content that maintains their structural integrity under crushing force. The cellular adaptations to extreme pressure represent some of the most sophisticated biochemical engineering in the natural world. Deep-sea proteins are held together by additional molecular bonds that prevent them from unfolding under pressure. The cell membranes of abyssal creatures contain specialized lipids that remain flexible and functional despite the enormous forces pressing upon them. Some deep-sea bacteria have evolved pressure-sensing mechanisms so sensitive they can detect minute changes in depth, allowing them to maintain their optimal position in the water column with extraordinary precision. The metabolic processes of deep-sea life operate under constraints that would challenge any surface organism. With food scarce and energy precious, many creatures have evolved the ability to slow their biological processes to near-suspended animation when resources are unavailable. The deep-sea giant isopod, a crustacean related to terrestrial pillbugs, can survive without food for over 5 years by reducing its metabolic rate to barely detectable levels. During these extended fasting periods, the animal enters a state of dormancy so profound that it appears lifeless, yet remains ready to spring into activity the moment prey becomes available. The bioluminescent bacteria that live within many deep-sea animals have formed partnerships so intimate that the boundaries between host and symbiont become blurred. These bacterial communities not only provide light for their hosts, but also contribute to their nutrition, chemical defense, and even waste processing. In return, the host animals provide their bacterial partners with nutrients, protection, and optimal conditions for growth. Some deep-sea fish carry such diverse communities of bioluminescent bacteria that their light organs function like living laboratories, each species of bacteria contributing different colors and intensities to create complex light displays. The hunting strategies employed in the abyss reveal the extreme measures life takes when every calorie counts. The deep-sea anglerfish has evolved jaws that can dislocate to accommodate prey larger than the predator itself. Once prey is captured, the fish's expandable stomach can stretch to several times its normal size, allowing the anglerfish to store an entire meal that might sustain it for months. The digestive process in these creatures has slowed to match their environment, with some deep-sea fish taking weeks to fully process a single large meal. The barrel-eye fish represents one of the most extraordinary visual adaptations in the deep sea. This remarkable creature has evolved a transparent head filled with fluid, within which its tubular eyes can rotate freely. These eyes are permanently fixed upward, scanning the water above for the silhouettes of prey against the faint downwelling light. When the fish spots a potential meal, it can rotate its entire body to align its mouth with its upward-pointing eyes, a hunting strategy so specialized it seems engineered for the specific conditions of the deep ocean twilight zone. The reproductive challenges of the deep sea have driven some of the most unusual mating behaviors in the animal kingdom. Many deep-sea creatures are hermaphroditic, carrying both male and female reproductive organs to maximize their chances of successful reproduction when encounters with others of their species are rare. Some deep-sea squid have evolved specialized arms that can detach from the male's body and swim independently to locate and fertilize females, essentially turning reproduction into a remote-controlled process. The seasonal migrations that occur in the deep sea rival any terrestrial animal movement in their scale and precision. The daily vertical migration of countless small organisms creates a biological elevator system that transports nutrients and energy between the surface and the depths. Some deep-sea creatures time their entire life cycles to these migrations, positioning themselves at specific depths during certain seasons to intercept the maximum amount of food as it passes through their layer of the ocean. The chemical environment of the deep sea creates opportunities for life forms that exist nowhere else on our planet. Around cold seeps, where chemicals leak slowly from the seafloor, entire ecosystems have evolved to exploit these mineral-rich waters. Tube worms cluster around these seeps in vast meadows, their bodies filtering the chemical-laden water to extract the compounds their bacterial symbionts need for chemosynthesis. These cold seep communities can persist for decades or even centuries, creating stable oases of life in the otherwise food-poor deep ocean. The architecture of hydrothermal vent communities rivals the complexity of any terrestrial ecosystem. Different species occupy distinct zones around the vents, each adapted to specific temperature and chemical gradients. The areas closest to the vent openings, where temperatures can exceed the boiling point of water at sea level, are colonized by specialized bacteria that form thick mats of living tissue. These bacterial mats provide food for grazing organisms like vent limpets and scale worms, which have evolved heat-resistant shells and protective coverings. In the intermediate zones around hydrothermal vents, where temperatures moderate to merely scalding, larger organisms create complex, three-dimensional habitats. Vent mussels attach themselves to the rocky surfaces in dense clusters, their shells providing attachment sites for other organisms in a biological cascade that builds upward from the seafloor. Some vent communities develop into structures resembling underwater cities, with towering spires of tube worms creating a canopy above the seafloor, while smaller organisms fill every available niche in the spaces between. The chemistry of vent waters varies dramatically between different locations, and the life forms that colonize each vent system reflect these chemical differences. Some vents produce water rich in hydrogen sulfide, supporting communities dominated by sulfur-processing bacteria and their animal partners. Other vents emit water containing high concentrations of methane, creating ecosystems based on methane-consuming microorganisms. The most exotic vents produce water containing dissolved metals and rare elements, supporting bacterial communities that can literally eat rock and metal compounds. The discovery of life around hydrothermal vents revolutionized our understanding of the requirements for life itself. These ecosystems demonstrate that complex communities can exist entirely independent of solar energy, deriving all their energy from geological processes. The implications of this discovery extend far beyond Earth. suggesting that life might exist in the subsurface oceans of ice-covered moons like Europa and Enceladus, where tidal heating could drive similar hydrothermal processes. The genetic diversity found in hydrothermal vent communities often exceeds that of tropical rainforests, despite the apparent simplicity of the physical environment. Each vent system acts as an isolated island of life, allowing species to evolve independently over geological timescales. When vents become inactive and their communities die out, new vents that form nearby are colonized by larvae and spores that drift through the deep ocean currents, beginning the process of evolution and adaptation anew. The pressure effects on hydrothermal vent chemistry create conditions unlike anywhere else on Earth. The extreme pressure prevents water from boiling even at temperatures that would instantly vaporize surface water, allowing liquid water to exist at temperatures exceeding 400 degrees Celsius. This superheated water can dissolve minerals and chemicals that remain insoluble under normal conditions, creating chemical soups rich in compounds that can fuel chemosynthetic life. The symbiotic relationships that form the foundation of vent ecosystems represent some of the most intimate partnerships in the natural world. The giant tube worms that dominate many vent communities have no digestive system whatsoever, instead relying entirely on the bacteria living within their tissues. These worms actively pump vent water through their bodies, providing their bacterial partners with the chemicals they need while absorbing the organic compounds the bacteria produce in return. The relationship is so complete that neither organism can survive without the other. The life cycles of vent organisms are precisely timed to the geological rhythms of their environment. Most hydrothermal vents remain active for only a few decades before the underground plumbing that feeds them shifts or becomes blocked. The organisms living around these vents have evolved rapid growth rates and early reproductive maturity, ensuring they can complete multiple generations before their habitat disappears. When a vent dies, the specialized organisms that depended on it die with it, but their larvae may already be dispersing through the deep ocean currents in search of new active vents to colonize. The study of hydrothermal vent ecosystems has revealed biochemical processes that challenge our understanding of life's limits. Some vent bacteria can survive direct exposure to temperatures that would sterilize most environments, while others can metabolize compounds so toxic they would kill conventional organisms instantly. These extremophile organisms have evolved enzymes and cellular machinery that not only tolerate extreme conditions, but actually require them to function properly. The magnetic properties of some hydrothermal vent minerals create unique navigational challenges and opportunities for the organisms living there. Some vent animals have evolved magnetic sensors that help them navigate the complex three-dimensional landscape around active vents, while others use magnetic fields to detect the presence of metal-rich vent waters from great distances. The interaction between biology and geology at these sites creates feedback loops where living organisms actually modify the mineral formations that support them. The deep-sea mining potential of hydrothermal vent sites has created new conservation challenges for these unique ecosystems. The mineral-rich deposits that form around active and extinct vents contain concentrations of rare metals and elements valuable for human technology, but extracting these resources would destroy habitat types found nowhere else on Earth. The organisms that live around these vents may hold keys to biotechnological applications we haven't yet imagined, from heat-resistant enzymes to novel approaches to metal processing and waste remediation. The pressure gradients that exist around hydrothermal vents create microenvironments with dramatically different physical and chemical conditions within distances of mere meters. Some organisms have evolved the ability to move between these microenvironments, essentially traveling between different worlds within the space of a few body lengths. The thermal boundaries around vents can be so sharp that an organism's head might experience temperatures comfortable for surface life, while its tail remains in near boiling water. The acoustic environment around hydrothermal vents differs dramatically from the rest of the deep sea. The bubbling and hissing of superheated water creates a constant soundscape that some vent organisms may use for navigation and communication. The high mineral content of vent water also affects how sound travels, creating acoustic shadows and reflection patterns that could serve as landmarks for creatures navigating in absolute darkness. The evolutionary history preserved in vent communities provides insights into how life might have originated on early Earth. Some scientists theorize that life itself may have first evolved around ancient hydrothermal vents, where the chemical energy and protective environment could have supported the earliest self-replicating molecules. The biochemical pathways used by modern vent organisms may represent evolutionary echoes of these primordial life processes. The interconnections between different vent sites across the global ocean create a hidden network of gene flow and species exchange that operates on geological timescales. Larvae produced at one vent system may drift for months through deep ocean currents before settling at a vent hundreds of kilometers away. This dispersal process maintains genetic diversity across vent populations while allowing for the colonization of newly formed vent sites. The seasonal variations that affect even the deepest parts of the ocean influence hydrothermal vent communities in subtle but important ways. Changes in deep water circulation patterns can alter the flow of nutrients to vent sites, while variations in the strength of deep ocean currents can affect larval dispersal between vents. Some vent organisms appear to time their reproductive cycles to these deep ocean seasons, maximizing their chances of successful larval dispersal and settlement. The chemical signatures produced by different types of hydrothermal vents create distinct biological fingerprints that allow scientists to identify and classify vent communities from great distances. The ratios of different dissolved compounds in vent water correlate with specific types of bacterial communities, which in turn support characteristic assemblages of larger organisms. This chemical biological coupling means that understanding the geology of a vent site can predict the types of life forms that will be found there. The biomineralization processes that occur around hydrothermal vents involve complex interactions between living organisms and geological processes. Some vent bacteria actually precipitate mineral formations as part of their metabolism, creating structures that become incorporated into the geological architecture of the vent site. These biologically mediated mineral formations can persist long after the organisms that created them have died, leaving signatures of ancient biological activity preserved in the rock record. The energy flow through hydrothermal vent ecosystems follows pathways unlike any other ecosystem on Earth. Primary production occurs not through photosynthesis, but through chemosynthesis, with bacteria converting chemical energy directly into biological energy. This energy then flows upward through food webs that can include dozens of trophic levels, from grazing organisms that feed on bacterial mats to predatory fish and crustaceans that hunt in the warm waters around active vents. The adaptation strategies employed by vent organisms demonstrate evolution's ability to find solutions to seemingly impossible challenges. Heat shock proteins that prevent cellular damage at high temperatures, specialized enzymes that function optimally under extreme pressure, and symbiotic relationships that allow organisms to exploit toxic chemical environments all represent evolutionary innovations that have emerged from the unique selective pressures of the hydrothermal vent environment. As we continue our exploration through these remarkable deep-sea oases, we encounter communities that exist at the very limits of life as we understand it. Each vent system represents a unique experiment in evolution, an isolated laboratory where life has found new ways to harness the planet's geological energy and transform it into the complex web of relationships that characterize all thriving ecosystems, iving ecosystems. The twilight realm between the surface and the true abyss holds creatures that seem crafted from dreams and starlight. Here, the vampire squid drifts through liquid space with movements so graceful they appear choreographed. Despite its ominous name, this gentle creature feeds not on blood, but on the constant gentle snowfall of organic particles that rain down from the sunlit world above. When threatened, it performs one of the ocean's most extraordinary defensive displays, turning itself completely inside out to reveal rows of protective spines, while simultaneously releasing clouds of bioluminescent mucus. that create a galaxy of blue sparks in the surrounding water. The deep sea's most accomplished architects are perhaps the colonial siphonophores, creatures that challenge our very definition of what constitutes an individual organism. These living strings of pearls can stretch for hundreds of meters through the water column, each pearl a specialized individual organism working in perfect harmony with thousands of others. Some members of the colony are dedicated to locomotion, others to feeding, and still others to reproduction. Yet they function as a single entity with a coordination that surpasses any human orchestra. Their bioluminescent displays ripple along their entire length like messages written in living light, creating patterns so complex that scientists are only beginning to decode their meaning. In the perpetual midnight of the bathypelagic zone, the giant isopods patrol the seafloor like armored sentinels from another world. These crustaceans, related to the humble pillbugs found in terrestrial gardens, have grown to extraordinary proportions in the deep sea, some reaching lengths of over half a meter. Their survival strategy centers on extreme patience and energy conservation. When food is scarce, which is most of the time in these depths, they can enter a state of near-suspended animation that can last for years, their metabolic processes slowing to barely detectable levels while they wait for the next meal to arrive. The pressure at these depths creates a world where the normal rules of physics seem suspended. Gas-filled organs that work perfectly at the surface would collapse instantly here, yet life has found remarkable workarounds. Many deep-sea fish have replaced their gas-filled swim bladders with oil-filled organs that provide buoyancy without the risk of compression. These oils have specific densities that allow precise depth control, enabling creatures to maintain their position in the water column with minimal energy expenditure. Some species can adjust the composition of these oils seasonally, fine-tuning their buoyancy as water density changes with temperature and salinity variations. The bioluminescent bacteria that form partnerships with deep-sea animals have evolved into some of nature's most sophisticated living laboratories. These microorganisms don't simply produce light, they create complex chemical environments within their host's tissues that can serve multiple functions simultaneously. Some bacterial communities produce not only illumination, but also antibiotics that protect their hosts from infection, digestive enzymes that help process food, and even chemical signals that may play roles in reproduction and territorial behavior. The relationship between host and bacteria becomes so intimate that the boundaries between the two organisms blur, creating what scientists call a holobiont, a single functional unit composed of multiple species. The hunting strategies employed in these lightless depths reveal evolution's creativity when faced with extreme scarcity. The deep-sea dragonfish has evolved a bioluminescent lure so sophisticated it can produce multiple colors and patterns of light, each designed to attract different types of prey. But perhaps most remarkably, this predator has evolved the ability to see red light while producing it invisibly to most other deep-sea creatures. This creates a private communication channel that allows dragonfish to illuminate their prey without alerting it to danger, like using infrared night vision in a world where no one else can see beyond the blue-green spectrum. The bizarre mating adaptations of deep-sea anglerfishes represent perhaps the most extreme sexual dimorphism in the animal kingdom. While the females grow into fearsome predators the size of footballs, the males remain tiny throughout their lives, sometimes smaller than the female's lure. When a male encounters a female, he bites into her flesh and begins a process of tissue fusion so complete that his circulatory system merges with hers. Eventually, the male becomes nothing more than a reproductive appendage, his entire body dedicated to producing sperm when the female is ready to spawn. Some females carry multiple fused males, ensuring reproductive success in an environment where encounters between individuals are extraordinarily rare. The pressure effects on biochemistry in the deep sea have driven some of the most remarkable molecular adaptations known to science. The proteins that make up deep sea organisms must maintain their structure and function under pressures that would denature surface proteins instantly. These pressure-adapted proteins often have additional chemical bonds and altered amino acid sequences that actually make them more stable under extreme pressure than at surface conditions. Some deep-sea enzymes become more efficient as pressure increases, turning what seems like a hostile environment into an advantage for the organisms that have evolved to exploit it. The vertical migration patterns that occur daily in the deep ocean create biological elevators that transport energy and nutrients between different layers of the sea. This migration involves billions of small organisms rising toward the surface at night to feed, then returning to the safety of the depths before dawn. The scale of this movement is so vast that it was initially detected by naval sonar operators who thought they had discovered a false seafloor that mysteriously moved up and down with the daily cycle. This great migration creates feeding opportunities for deep-sea predators that time their hunting activities to intercept the migrating masses. The chemosynthetic oases that surround hydrothermal vents create ecosystems so alien they seem transplanted from another planet. Here, towering chimneys of mineral deposits spew superheated water rich in chemicals that would be toxic to most surface life. Yet these harsh conditions support some of the most abundant and diverse communities in the deep ocean. Giant tube worms cluster around the vent openings like underwater redwoods, their crimson plumes filtering the chemical-rich water to extract the compounds their bacterial symbionts need for survival. The bacterial communities that form the foundation of vent ecosystems have evolved biochemical pathways that seem to violate the basic principles of biology as understood from surface life. These microorganisms can derive energy from hydrogen sulfide, a compound so toxic it would kill most organisms instantly, while others metabolize methane, ammonia, or even dissolved metals. Some vent bacteria can survive direct contact with water hot enough to melt lead, their cellular machinery protected by specialized proteins and membrane structures that remain stable at temperatures that would sterilize most environments. The three-dimensional architecture of mature vent communities creates complex habitats that support dozens of specialized species. Vent mussels attach themselves to rocky surfaces in dense aggregations, their shells providing substrate for other organisms in a biological cascade that builds upward from the seafloor. Vent crabs scuttle through this underwater city, their specialized appendages equipped with chemical sensors that allow them to detect the optimal zones of temperature and chemistry around the vents. Some of these crabs have evolved such specific adaptations to vent life that they cannot survive in normal seawater, their physiology completely dependent on the unique chemistry of their hydrothermal habitat. The life cycles of vent organisms are synchronized to the geological rhythms of their environment in ways that demonstrate evolution's ability to adapt to the most unusual selective pressures. Most hydrothermal vents remain active for only a few decades before the underground plumbing that feeds them shifts or becomes blocked. The organisms that depend on these ephemeral oases have evolved rapid growth rates and early reproductive maturity, ensuring they can complete multiple generations before their habitat disappears. When a vent system dies, its specialized communities die with it, but by then, countless larvae have already dispersed into the deep ocean currents, searching for new active vents to colonize. The dispersal of vent larvae through the deep ocean creates a hidden network of genetic exchange that operates on timescales measured in decades and distances measured in hundreds of kilometers. These larvae can drift for months in the deep currents, their development arrested in a state of suspended animation until they encounter the chemical signatures that indicate the presence of an active vent system. The ability to detect these chemical cues from great distances allows larvae to locate suitable habitat in the vast emptiness of the deep ocean, though the majority will never find a new home and will eventually exhaust their energy reserves in the endless search. The mineral formations created by hydrothermal vent activity interact with biological processes in ways that blur the boundaries between living and non-living systems. Some vent bacteria actually precipitate mineral structures as part of their metabolic processes, creating formations that become incorporated into the geological architecture of the vent site. These biologically mediated minerals can preserve evidence of ancient life long after the organisms that created them have vanished, leaving fossils of communities that thrived around vents millions of years ago. The acoustic environment around active hydrothermal vents differs dramatically from the profound silence that characterizes most of the deep ocean. The constant hissing and bubbling of superheated water creates a soundscape that some vent organisms may use for navigation and communication. The high mineral content of vent water affects how sound travels, creating acoustic shadows and reflection patterns that could serve as auditory landmarks for creatures moving through the complex three-dimensional landscape around active vents. The chemical gradients that exist around hydrothermal vents create microenvironments with dramatically different conditions within the space of mere meters. Some organisms have evolved the remarkable ability to move between these microenvironments, essentially traveling between different worlds within the span of a few body lengths. The Pompeii worm exemplifies this adaptation, living with its tail in water hot enough to kill most complex organisms, while keeping its head in cooler water that approaches the temperature range tolerable to surface life. The evolutionary relationships between different vent communities reveal how isolation and similar selective pressures can lead to convergent evolution on a global scale. Vent systems in different ocean basins often support communities that look remarkably similar, despite being composed of completely different species that have evolved independently for millions of years. This convergent evolution demonstrates how the unique chemistry and physics of hydrothermal vents create such specific selective pressures that life responds with similar solutions regardless of its evolutionary starting point. The cold seeps that occur in other parts of the deep sea floor represent a slower, gentler version of hydrothermal vent ecosystems. Here, chemicals leak gradually from the sediments over periods of decades or centuries, creating stable oases of chemosynthetic life that can persist far longer than the ephemeral hydrothermal vents. The tube worm meadows that surround cold seeps can extend for hundreds of meters across the seafloor, their root-like structures penetrating deep into the sediments to access the chemical-rich fluids below. The deep-sea mushes that form around whale falls create temporary islands of abundance in the nutrient-poor abyss, supporting specialized communities found nowhere else on Earth. These massive carcasses progress through distinct stages of decomposition, each supporting different assemblages of organisms, adapted to exploit specific aspects of the decaying whale. The bone-eating stage can last for decades, during which specialized worms literally dissolve the whale's skeleton from within, their bodies adapted to digest calcium phosphate and extract the lipids stored in the bones. The glass sponge reefs that grow in some deep-sea areas create three-dimensional habitats that can persist for thousands of years, their delicate silicate skeletons forming complex frameworks that support diverse communities of fish, crustaceans, and other invertebrates. These ancient organisms grow so slowly that individual sponges may live for millennia, their skeletons serving as archives of environmental conditions over geological timescales. Some glass sponge reefs are thought to be among the oldest continuously existing animal communities on Earth. The bioluminescent displays that illuminate the deep ocean serve purposes far more complex than simple communication or predation. Some creatures use coordinated, flashing patterns to create the illusion of larger organisms, deterring predators through deceptive displays that make them appear more formidable than they actually are. Others use bioluminescence as a form of camouflage, producing light on their undersides that matches the faint, downwelling radiance from above, effectively erasing their silhouettes when viewed from below. The deep scattering layer phenomenon creates one of the ocean's most spectacular daily light shows, as billions of small organisms migrate vertically through the water column in synchronized movements that can be detected by sonar from the surface. During these migrations, the water column fills with so much bioluminescence that the ocean appears to glow from within, creating displays that early explorers described as underwater auroras or liquid starfields moving through the depths. As we drift through these deepest waters, surrounded by creatures that seem assembled from light and shadow, we begin to understand that the deep ocean is not a single environment, but a complex mosaic of interconnected habitats, each supporting life forms adapted to conditions that challenge our understanding of what organisms can endure. From the crushing pressures of the deepest trenches to the scalding waters of hydrothermal vents, life has found ways not merely to survive, but to create some of the most beautiful and complex ecosystems on our planet. The profound silence of the abyss is punctuated only by the gentle movements of creatures perfectly adapted to their liquid world, their bioluminescent signals creating temporary constellations in the darkness before fading back into the eternal night. Here, in this realm that receives no light from the sun and no warmth from the surface, life has learned to make its own light and find its own sources of energy, creating communities that exist entirely independent of the photosynthetic world we know. The evolutionary arms race between predator and prey in the deep ocean has produced some of the most extraordinary examples of biological innovation on Earth. In this realm, where energy is precious and encounters are rare, every adaptation must serve multiple purposes, leading to creatures that seem to have been designed by committee between function and fantasy. The deep-sea hatchetfish exemplifies this evolutionary efficiency, its silvery body equipped with rows of photophores that can be individually controlled to create complex patterns of light and shadow. These living mirrors have mastered the art of optical camouflage in 3 dimensions. Their photophores don't simply produce light randomly, but are precisely calibrated to match the intensity and angle of any faint illumination filtering down from above. As the fish moves through different depths, it continuously adjusts its bioluminescent output to maintain perfect invisibility against the subtle backdrop of the water column. This counter-illumination camouflage is so sophisticated that the fish can remain virtually undetectable, even when viewed from directly below by predators scanning the waters above. The pressure adaptations required for life in the deep ocean extend far beyond simple structural modifications. At depths where the water pressure exceeds 1,000 times that at sea level, the very chemistry of life must be reimagined. The cellular membranes of abyssal creatures contain specialized lipids that remain flexible under crushing pressure, while their proteins are stabilized by additional molecular bonds that prevent them from unfolding under extreme force. Some deep-sea organisms have evolved pressure-sensing mechanisms so sensitive they can detect minute changes in depth, allowing them to maintain optimal positions in the water column with remarkable precision. The barotrauma that would instantly kill surface organisms becomes irrelevant to creatures whose entire physiology has been shaped by extreme pressure. Their bodies contain no gas-filled spaces that could collapse, and their internal fluids are at the same pressure as the surrounding water. When brought rapidly to the surface, these creatures experience the reverse problem: their pressure-adapted proteins becoming unstable, and their specialized cellular machinery failing to function in the low-pressure environment that surface life takes for granted. The reproductive strategies of deep-sea creatures reflect the challenges of finding mates in an environment where population densities are measured in individuals per cubic kilometer rather than per square meter. Many species have evolved hermaphroditic capabilities, carrying both male and female reproductive organs to maximize the chances of successful reproduction during the rare encounters with others of their kind. Some deep-sea squid have developed reproductive strategies so unusual they border on science fiction, with specialized reproductive arms that can detach from the male's body and swim independently to locate and fertilize females. The bioluminescent courtship displays of the deep ocean rival any terrestrial mating ritual in their complexity and beauty. Deep-sea squid create elaborate light shows across their bodies, with waves of color and pattern that may communicate species identity, reproductive readiness, and individual quality. These displays must be carefully calibrated to be visible to potential mates while avoiding detection by predators, leading to signaling systems that operate like underwater semaphore in frequencies and patterns that only the intended recipients can interpret. The energy economics of the deep sea have shaped feeding behaviors that seem almost mathematical in their precision. Every movement, every metabolic process Every decision to pursue potential prey must be weighed against the energy cost and the probability of success. The deep-sea anglerfish has evolved what may be the most energy-efficient hunting strategy in the animal kingdom, remaining motionless for months at a time while its bioluminescent lure does all the work of attracting prey. The energy saved by this passive hunting approach allows the fish to invest more resources in growth and reproduction, creating a survival strategy based on patience rather than activity. The bacterial communities that live within deep-sea animals have evolved into biological factories of extraordinary sophistication. These microbial partners don't simply produce light for their hosts, but create complex chemical environments that can serve multiple functions simultaneously. Some bacterial communities produce antibiotics that protect their hosts from infection in an environment where any wound could prove fatal. Others manufacture enzymes that help digest the unusual prey items that form the bulk of deep-sea diets, breaking down chitin, bone, and other materials that would be indigestible to most surface animals. The symbiotic relationships between deep-sea animals and their bacterial partners represent some of the most intimate biological partnerships known to science. In many cases, the bacteria are passed from generation to generation through the host's eggs, ensuring that offspring are born with their essential microbial partners already in place. Some deep-sea fish have evolved specialized organs that function as bacterial cultivation chambers, providing optimal conditions for their microbial partners while harvesting the light and chemical products they produce. The hydrothermal vent ecosystems scattered across the deep ocean floor represent oases of abundance in the vast desert of the abyss. These underwater geysers create chemical environments so extreme they seem hostile to life, yet they support some of the most productive ecosystems in the deep ocean. The water streaming from these vents contains concentrations of hydrogen sulfide, methane, and heavy metals that would be instantly lethal to most surface organisms. Yet the bacteria that colonize these sites have evolved to use these toxic compounds as energy sources. The architecture of mature hydrothermal vent communities creates complex three-dimensional habitats that support remarkable diversity within very small areas. The zonation around active vents is determined by precise gradients of temperature and chemistry, with different species occupying narrow bands where conditions fall within their specific tolerance ranges. The giant tube worms that dominate many vent sites position themselves in zones where the water is hot enough to support their bacterial symbionts, but cool enough to prevent protein denaturation in their own tissues. The Pompeii worms that live closest to the vent openings have evolved perhaps the most extreme temperature tolerance of any complex animal. These remarkable creatures can survive with their tail ends in water exceeding 80 degrees Celsius, while keeping their heads in relatively cool water around 20 degrees. They achieve this incredible feat through a combination of specialized proteins, protective bacterial coatings, and behavioral adaptations that allow them to exploit the steepest thermal gradients on Earth. The vent crabs that scuttle through these underwater oases have evolved sensory systems specifically adapted to navigate the complex chemical and thermal landscape around active vents. Their legs are equipped with chemoreceptors that can detect minute differences in water chemistry, allowing them to locate optimal feeding areas and avoid zones of lethal temperature or toxicity. Some species have evolved heat-resistant shells and specialized hemoglobin that remains functional at temperatures that would denature the blood proteins of surface crustaceans. The dispersal mechanisms that allow vent organisms to colonize new sites represent some of the most remarkable long-distance migration strategies in the animal kingdom. The larvae of vent species can remain viable for months while drifting through the deep ocean currents, their development arrested in a state of suspended animation until they encounter the chemical signatures that indicate the presence of an active vent system. The ability to detect these chemical cues from distances of kilometers allows larvae to locate suitable habitat in the vast emptiness of the deep ocean. The geological processes that create and destroy hydrothermal vents operate on timescales that have profoundly influenced the evolution of vent communities. Most individual vents remain active for only a few decades before the underground plumbing that feeds them shifts or becomes blocked. This geological instability has driven the evolution of organisms with rapid growth rates, early reproductive maturity, and highly efficient dispersal mechanisms. The entire life history strategy of vent organisms is shaped by the knowledge that their habitat is temporary. The chemical signatures produced by different types of hydrothermal vents create distinct biological fingerprints that determine which species can colonize each site. Vents that produce water rich in hydrogen sulfide support communities, dominated by sulfur-oxidizing bacteria and their animal partners, while those that emit methane-rich water foster ecosystems based on methane-consuming microorganisms. The most unusual vents produce water containing high concentrations of dissolved metals, supporting bacterial communities that can literally metabolize rock and mineral compounds. The biomineralization processes that occur around hydrothermal vents create structures that blur the boundary between biology and geology. Some vent bacteria actively precipitate mineral formations as part of their metabolic processes, creating chimney-like structures that become incorporated into the geological architecture of the vent site. These biologically mediated minerals can preserve evidence of ancient biological activity long after the organisms that created them have vanished, creating fossils that record the history of life in the deep ocean. The pressure effects on hydrothermal vent chemistry create conditions that exist nowhere else on Earth. The extreme pressure prevents water from boiling, even at temperatures exceeding 400 degrees Celsius, allowing liquid water to exist at temperatures that would instantly vaporize surface water. This superheated liquid can dissolve minerals and chemicals that remain insoluble under normal conditions, creating chemical environments of unprecedented richness and complexity. The acoustic environment around active hydrothermal vents provides another layer of sensory information that vent organisms have learned to exploit. The constant hissing and bubbling of superheated water creates distinctive sound signatures that may help organisms navigate the complex landscape around active vents. Some vent animals have evolved enhanced acoustic sensitivity that allows them to detect the subtle sound patterns that indicate optimal feeding or shelter sites within the vent complex. The magnetic properties of hydrothermal vent minerals create unique navigational challenges and opportunities for the organisms that live there. The high concentrations of iron and other magnetic minerals in vent water and precipitates create local magnetic anomalies that some organisms may use as landmarks for navigation. The interaction between these magnetic fields and the Earth's magnetic field creates complex patterns that could provide navigation cues for organisms moving between different vent sites. The cold seep ecosystems that occur in other parts of the deep sea floor represent a gentler, more stable version of hydrothermal vent communities. These sites, where chemicals leak slowly from the sediments over periods of decades or centuries, support communities that can persist far longer than the ephemeral hydrothermal vents. The tube worm meadows that surround cold seeps can extend for hundreds of meters across the seafloor, creating some of the largest continuous biological structures in the deep ocean. The whale-fall communities that develop around the carcasses of large marine mammals create temporary islands of abundance that support some of the most specialized organisms in the deep sea. These massive food sources progress through distinct stages of decomposition, each supporting different assemblages of creatures adapted to exploit specific aspects of the decaying whale. The bone-eating phase, which can last for decades, supports worms that have evolved the remarkable ability to digest solid bone, dissolving calcium phosphate to extract the lipids stored within the whale's skeleton. The deep-sea wood, falls that occur when terrestrial plant material sinks to the ocean floor, create yet another type of specialized community. The bacteria and fungi that colonize these wooden substrates must adapt to the high-pressure, low-oxygen environment of the deep sea, while maintaining their ability to break down the complex lignins and celluloses that make up wood. These decomposer communities support grazing organisms that have evolved specifically to exploit this unusual food source. The glass sponge reefs that grow in some deep-sea areas create three-dimensional habitats that can persist for thousands of years. These ancient organisms build their skeletons from intricate frameworks of silica spicules, creating structures of extraordinary beauty and complexity. Individual glass sponges can live for millennia, growing so slowly that they add new material to their skeletons at rates measured in millimeters per decade. The accumulated skeletons of dead sponges create reef-like structures that provide habitat for diverse communities of fish, crustaceans, and other invertebrates. The bioluminescent displays that occur during deep-sea feeding frenzies create some of the most spectacular light shows in the natural world. When a large food source, like a whale fall or a massive jellyfish, attracts multiple predators and scavengers, the resulting bioluminescent activity can be visible from great distances. These feeding aggregations create temporary hotspots of biological activity in the otherwise sparse deep ocean, drawing organisms from across the surrounding area in a cascade of attraction and predation. The seasonal variations that affect deep-sea communities operate on timescales and through mechanisms very different from those that drive surface ecosystems. The daily vertical migrations of small organisms create predictable pulses of food availability that deep-sea predators have learned to anticipate and exploit. Some abyssal creatures time their reproductive cycles to these subtle rhythms, ensuring their offspring hatch when food is most likely to be available. The pressure wave signatures generated by major surface storms can travel to the deepest parts of the ocean, creating subtle current changes that deep-sea organisms can detect and respond to. These pressure pulses may serve as seasonal cues for creatures living in environments where traditional markers of seasonal change are absent or greatly attenuated. The ability to sense these distant surface events allows deep-sea organisms to remain connected to the larger rhythms of ocean productivity, even in their isolated abyssal habitats. The deep ocean's role in global biogeochemical cycles extends far beyond simple carbon storage. The vast water masses that flow through abyssal plains carry dissolved nutrients, trace elements, and organic compounds across ocean basins, creating chemical connections between distant ecosystems. The organisms living in these deep currents help process and transform these materials as they travel, influencing ocean chemistry on a global scale. The microbial communities that live within deep-sea sediments represent some of the most patient organisms on Earth. With metabolism so slow they may divide only once every 1,000 years, these bacteria exist in a state that challenges our definitions of active life. Yet they maintain their cellular integrity across geological timescales, persisting in environments that remain stable for millions of years while processing organic matter at rates so slow they are barely detectable. The biotechnology potential of deep-sea organisms continues to reveal new applications that could benefit human society, while highlighting the intrinsic value of these remarkable ecosystems. The pressure-resistant enzymes found in abyssal bacteria could revolutionize industrial processes that require high-pressure conditions, while the efficient bioluminescent systems of deep-sea creatures offer models for new lighting technologies that consume minimal energy while producing maximum illumination. The conservation challenges facing deep-sea ecosystems are becoming increasingly urgent as human activities reach into previously untouched parts of the ocean. Deep-sea mining threatens to disturb seafloor communities that have remained unchanged for millions of years, while climate change is altering the chemistry and circulation patterns of deep waters in ways that could profoundly impact these ancient ecosystems. The slow growth rates and specialized adaptations of deep-sea organisms make them particularly vulnerable to rapid environmental changes. The interconnected nature of deep-sea ecosystems means that disturbances in one area can have cascading effects across vast regions of the ocean. The disruption of a single hydrothermal vent field could eliminate species found nowhere else on Earth, while changes in deep water circulation could affect the food supply for organisms thousands of kilometers away. Understanding these connections is crucial for developing effective conservation strategies for the deep ocean. The exploration of the deep ocean continues to reveal new insights into the limits and possibilities of life on Earth. Each expedition to these remote waters discovers new species, new adaptations, and new ecological relationships that expand our understanding of biology and evolution. The deep ocean remains our planet's last great wilderness, a realm where new discoveries await in the darkness beyond our current reach. As we drift through these deepest waters, surrounded by creatures that have transformed the challenges of extreme pressure, perpetual darkness, and scarce food into opportunities for extraordinary beauty and complexity, we begin to appreciate the deep ocean not as a hostile wilderness, but as a testament to life's infinite creativity. Here, in conditions that would seem impossible for life as we know it, entire civilizations of organisms have evolved ways not merely to survive, but to create some of the most intricate and beautiful ecosystems on our planet. The profound silence of the abyss speaks not of emptiness, but of patience, of life forms that have learned to thrive in harmony with pressures and temperatures that would crush or freeze the surface world we know. Their bioluminescent signals create temporary galaxies in the liquid darkness. Each flash a word in conversations we are only beginning to understand. Each pattern a story written in the universal language of living light that connects all life from the deepest trenches to the highest peaks of our remarkable planet. The dance of bioluminescence in the abyss follows rhythms older than continents, patterns of communication that have evolved over millions of years in the endless night. Some creatures have learned to speak in colors that shift and flow like underwater aurora, their bodies becoming living canvases where messages appear and dissolve in the span of heartbeats. The deep-sea jellies that drift through these waters carry within their translucent bells entire light shows, their radial canals lined with photophores that can cascade illumination from center to edge in waves that ripple outward like stones dropped in a dark pond. The colonial organisms of the deep have perhaps perfected bioluminescence beyond all others. These living chains of light can stretch through the water column like illuminated highways, each individual in the colony contributing its own small beacon to create displays visible across kilometers of open water. When disturbed, they produce coordinated flashes that travel along their entire length, creating the illusion of massive serpents made of starlight moving through the depths. The precision of these displays suggests a level of neural coordination that challenges our understanding of how colonial organisms can function as unified entities. The biochemistry that powers these living lights has been refined over evolutionary time to achieve efficiencies that surpass any human technology. The luciferin-luciferase reactions that create bioluminescence produce light without heat, converting chemical energy directly into photons with minimal waste. Some deep-sea creatures have evolved multiple types of luciferins, allowing them to produce different colors of light for different purposes. The blue-green light that dominates the deep ocean travels farthest through seawater, making it ideal for long-distance communication, while the rare red light produced by some species creates a private channel invisible to most deep-sea eyes. The pressure effects on these biochemical light factories create phenomena that exist nowhere else in nature. Under the crushing force of thousands of meters of water, the molecular reactions that produce bioluminescence actually become more efficient, the extreme pressure forcing molecules together in ways that enhance light production. This pressure enhancement may explain why bioluminescence is so much more common and diverse in the deep ocean than in surface waters, the abyss itself acting as a catalyst for these living light reactions. The hunting strategies that employ bioluminescence in the deep ocean demonstrate evolution's ability to turn light into a weapon of extraordinary sophistication. The deep-sea anglerfish has evolved lures that can produce not just steady glows, but complex patterns of flashing that mimic the bioluminescent signals of potential prey species. These counterfeit signals are so accurate they can fool creatures that have evolved alongside the real signals for millions of years, creating deadly games of deception played out in living light. Some predators have taken this deception even further, evolving the ability to produce bioluminescent displays that mimic entire schools of small fish. The loose-jaw fish can create patterns of light along its body that suggest the movement of multiple prey organisms, attracting larger predators that become prey themselves when they investigate what appears to be an easy meal. This biological theater of light and shadow creates predator-prey relationships of bewildering complexity where nothing is quite what it appears to be. The defensive uses of bioluminescence in the deep sea range from simple, startling flashes to elaborate deceptions that rival the most sophisticated military countermeasures. When attacked, many deep-sea creatures release clouds of bioluminescent particles or fluids, creating confusion screens that allow escape while potentially attracting larger predators that might threaten the original attacker. The deep-sea shrimp that produces luminous vomit when threatened essentially calls for help by creating a glowing beacon that advertises the presence of a disturbance to any larger predators in the area. The counter-illumination strategies employed by many midwater creatures represent perhaps the most sophisticated use of bioluminescence for camouflage. These animals produce precisely controlled light on their undersides that matches the intensity and angle of any faint illumination filtering down from above, effectively erasing their silhouettes when viewed from below. The photophores responsible for this camouflage can be individually controlled and continuously adjusted as the animal moves through different light conditions, creating an active camouflage system that responds in real time to changing environments. The social aspects of bioluminescence in the deep ocean create communities bound together by light-based communication systems of remarkable complexity. Some species of lanternfish use species-specific patterns of photophores to identify potential mates and rivals in the darkness, their light organs arranged in configurations as unique and recognizable as fingerprints. During spawning aggregations, these fish create underwater light shows that can be detected by submarines, thousands of individuals flashing in coordinated patterns that turn patches of deep ocean into temporary galaxies of biological stars. The pressure adaptations required for deep-sea life extend beyond simple structural modifications to encompass fundamental changes in how cellular machinery operates under extreme force. The proteins that make up deep-sea organisms are stabilized by additional chemical bonds and altered amino acid sequences that actually make them more stable under high pressure than at surface conditions. These pressure-adapted proteins often become non-functional when brought to lower pressures, their three-dimensional structures dependent on the crushing force of the deep ocean to maintain their proper shape. The cellular membranes of abyssal creatures contain specialized lipids that remain flexible and permeable under pressures that would solidify the membranes of surface organisms. These pressure-resistant membranes must maintain their selective permeability while withstanding forces that could compress normal cell membranes to a fraction of their functional thickness. The composition of these membranes changes with depth. Deep-sea organisms fine-tuning their cellular boundaries to match the specific pressure conditions of their habitat. The gas-filled organs that help surface fish control their buoyancy become impossible liabilities in the high-pressure environment of the deep ocean. Instead, many deep-sea fish have evolved oil-filled organs that provide neutral buoyancy without the risk of compression. These oils have precisely controlled densities that can be adjusted seasonally or even daily to maintain optimal buoyancy as water conditions change. Some species can alter the chemical composition of these oils to fine-tune their density, creating buoyancy control systems of remarkable precision. The pressure effects on gas solubility create unique physiological challenges for deep-sea organisms. Gases that remain safely dissolved in body fluids at depth can form dangerous bubbles if the animal experiences rapid pressure changes, a phenomenon similar to decompression sickness in human divers. Deep-sea fish have evolved circulatory and respiratory systems that minimize gas-filled spaces and use specialized proteins to keep essential gases in solution even under changing pressure conditions. The barotrauma that instantly kills surface organisms brought to depth becomes irrelevant to creatures whose entire physiology has been shaped by extreme pressure. Their bodies contain no compressible spaces, their internal pressures match those of their environment, and their biochemistry has evolved to function optimally under conditions that would crush surface life. When these creatures are brought to shallow water, they experience the reverse problem. Their pressure-adapted systems failing in the low-pressure environment that surface organisms take for granted. The hydrothermal vent ecosystems that dot the deep ocean floor create oases of chemical energy in the vast biological desert of the abyss. These underwater geysers spew superheated water rich in compounds that would be instantly lethal to most surface life, yet they support some of the most abundant and diverse communities in the deep ocean. The chemistry of vent waters varies dramatically between different sites, each creating unique selective pressures that have driven the evolution of highly specialized organisms found nowhere else on Earth. The bacterial communities that form the foundation of hydrothermal vent ecosystems have revolutionized our understanding of how life can derive energy from purely chemical sources. These chemosynthetic bacteria convert toxic compounds like hydrogen sulfide and methane into organic matter through processes that require no input from solar energy. The efficiency of these bacterial factories rivals and sometimes exceeds that of photosynthetic organisms, creating primary productivity in environments where photosynthesis is impossible. The symbiotic relationships between vent bacteria and their animal hosts represent some of the most intimate biological partnerships known to science. The giant tube worms that dominate many vent communities have completely eliminated their digestive systems, instead housing billions of chemosynthetic bacteria within specialized organs called trophosome. These bacterial partners convert the toxic chemicals in vent water into organic compounds that nourish their hosts, while the tube worms provide their bacteria with optimal chemical conditions and protection from the harsh vent environment. The three-dimensional architecture of mature vent communities creates complex ecosystems within very small areas, the biological equivalent of high-rise cities built around chemical factories. Different species occupy precise zones determined by gradients of temperature, chemistry, and water flow, with some organisms living literally centimeters away from conditions that would instantly kill them. The Pompeii worms that colonize the hottest areas around vent openings can survive with their posterior ends in water exceeding 80 degrees Celsius, while keeping their heads in relatively cool water, achieving this remarkable feat through specialized heat shock proteins and protective bacterial coatings. The vent crabs that scuttle through these underwater oases have evolved sensory systems specifically adapted to navigate the complex chemical and thermal landscape around active vents. Their appendages are equipped with chemoreceptors capable of detecting minute differences in water chemistry, allowing them to locate optimal feeding areas while avoiding zones of lethal temperature or toxicity. Some species have evolved such specific adaptations to vent chemistry that they cannot survive in normal seawater, their physiology completely dependent on the unique chemical environment of their hydrothermal habitat. The life cycles of vent organisms are precisely synchronized to the geological rhythms of their environment, their evolution shaped by the knowledge that their habitat is ephemeral. Most individual hydrothermal vents remain active for only a few decades before the underground plumbing that feeds them shifts or becomes blocked. This geological instability has driven the evolution of organisms with rapid growth rates, early reproductive maturity, and highly efficient dispersal mechanisms that allow them to colonize new vent sites as they become active. The dispersal of vent larvae through the deep ocean currents creates a hidden network of genetic exchange that operates across vast distances and geological timescales. These larvae can remain viable for months while drifting through the abyss, their development arrested in suspended animation until they encounter the distinctive chemical signatures that indicate the presence of an active vent system. The ability to detect these chemical cues from distances of many kilometers allows larvae to locate suitable habitat in the enormous emptiness of the deep ocean. Though the vast majority will exhaust their energy reserves in the search and never find a new home, the geological processes that create hydrothermal vents operate through the interaction of seawater with hot volcanic rock deep beneath the ocean floor. As seawater penetrates cracks in the seafloor, it is heated to extreme temperatures and becomes enriched with dissolved minerals and gases from the surrounding rock. This superheated, chemical-rich water then rises back to the seafloor under tremendous pressure, creating the dramatic underwater geysers that support vent communities. The mineral formations that build up around active hydrothermal vents create structures that blur the boundary between biology and geology. Some vent bacteria actively precipitate mineral chimneys as part of their metabolic processes, creating towering structures that can reach heights of tens of meters above the seafloor. These biological skyscrapers provide attachment surfaces for other organisms and help channel the flow of vent water in ways that create optimal conditions for different members of the vent community. The pressure effects on hydrothermal vent chemistry create conditions that exist nowhere else on Earth or in laboratory settings. The extreme pressure prevents water from boiling even at temperatures exceeding 400 degrees Celsius, allowing liquid water to exist at temperatures that would instantly flash to steam at surface pressure. This superheated liquid can dissolve minerals and chemicals that remain insoluble under normal conditions, creating chemical soups of unprecedented richness and complexity. The acoustic environment around active hydrothermal vents provides yet another layer of sensory information that vent organisms have learned to exploit for navigation and communication. The constant hissing and bubbling of superheated water creates distinctive sound signatures that vary with the activity level and chemical output of each vent. Some vent animals have evolved enhanced acoustic sensitivity that allows them to detect these subtle sound patterns and use them to locate optimal positions within the complex three-dimensional landscape of the vent field. The cold seep ecosystems that occur in other parts of the deep sea floor represent a more stable version of chemosynthetic communities, where chemicals leak slowly from sediments over periods of decades or centuries. These gentler chemical oases can support communities that persist far longer than the ephemeral hydrothermal vents, creating tube worm meadows that extend for hundreds of meters across the seafloor. The organisms in these communities have evolved different strategies from their vent cousins, emphasizing longevity and stability over the rapid growth and efficient dispersal required for life around temporary hydrothermal systems. The whale fall communities that develop around the carcasses of large marine mammals create temporary islands of abundance that support some of the most specialized decomposer communities in the ocean. These massive food sources progress through distinct ecological stages, each lasting years or decades, and supporting different assemblages of organisms adapted to exploit specific aspects of the decaying whale. The final bone-eating stage can persist for over a century, sustained by specialized worms that have evolved the remarkable ability to digest solid bone by dissolving calcium phosphate to extract the lipids stored within the whale's skeleton. The deep-sea wood falls that result from terrestrial plant material sinking to the abyssal depths create another type of specialized ecosystem based on chemosynthetic processes. The bacteria that colonize these wooden substrates must break down complex lignins and celluloses while adapting to the high-pressure, low-oxygen environment of the deep sea. These wood-degrading communities support unique assemblages of grazing organisms that have evolved specifically to exploit this unusual food source, creating biological islands around pieces of driftwood that may have traveled thousands of kilometers from their terrestrial origins. The glass sponge gardens that grow in some deep sea areas create three-dimensional reef-like structures that can persist for thousands of years. These ancient organisms build their skeletons from intricate frameworks of silica spicules, growing so slowly that individual sponges may live for millennia while adding new material at rates measured in millimeters per decade. The accumulated skeletons of countless generations create complex habitats that support diverse communities of fish, crustaceans, and other invertebrates, forming some of the most long-lived biological structures in the ocean. The bioluminescent plankton that populate the water column above these deep-sea communities create vertical connections between different layers of the ocean ecosystem. During their daily migrations toward the surface to feed, these organisms transport nutrients and energy between the productive surface waters and the food-poor depths. Their bioluminescent displays during these migrations create moving curtains of light that can be detected by deep-sea predators, who time their own activities to intercept these traveling food sources. The pressure gradients that exist in the water column create distinct zones where different adaptations are favored, leading to communities that change dramatically with depth, even over distances of a few hundred meters. The organisms that live at the boundaries between these zones often show remarkable physiological flexibility, able to tolerate the pressure changes that occur as they move between different parts of their habitat. Some deep-sea fish undertake daily vertical migrations that expose them to pressure changes equivalent to moving from sea level to the top of a mountain. Their bodies adapted to function across this entire range of conditions. The seasonal rhythms that penetrate even to the deepest parts of the ocean create subtle but important variations in the deep-sea environment. The daily vertical migrations of countless small organisms create predictable pulses of food availability that deep-sea predators have learned to anticipate and exploit. Some abyssal creatures time their reproductive cycles to these deep-sea seasons, ensuring their offspring hatch when food is most likely to be available in their energy-limited environment. As we continue our gentle descent through these remarkable depths, we encounter ecosystems that challenge every assumption about the requirements for abundant life. Communities that thrive in conditions that seem designed to prevent existence itself, yet have become some of the most productive and diverse habitats in our ocean's deepest reaches. The microscopic architects of the deep ocean floor work in scales so small they remain invisible to most eyes, yet their collective efforts reshape entire regions of the seafloor. These bacterial communities process organic matter at rates so slow they seem almost geological, breaking down the constant rain of marine snow, particle by particle, over periods that span decades. Their patient work creates chemical gradients in the sediment that support networks of larger organisms, from burrowing worms to sessile filter feeders that depend on the nutrients these microscopic recyclers make available. The bioturbation caused by deep-sea burrowing creatures creates three-dimensional highways through the sediment that allow water, nutrients, and dissolved gases to penetrate far deeper than would be possible through simple diffusion. These biological mixing processes, carried out by worms, crustaceans, and echinoderms, maintain the chemical balance of deep-sea sediments across vast areas of the ocean floor. The burrows themselves become microhabitats with their own distinct communities, supporting organisms that live nowhere else in the deep-sea environment. The chemoclines that develop at different depths within deep-sea sediments create layered ecosystems where different types of bacteria dominate at precise depths below the seafloor. These chemical boundaries can be as sharp as physical barriers, with completely different metabolic processes occurring within millimeters of each other. Some bacteria specialize in processing sulfur compounds, others focus on methane or nitrogen, creating a vertical stratification of biochemical processes that extends meters into the seafloor. The deep-sea mushroom phenomenon occurs when certain types of sediment bacteria form massive aggregations that can be seen from submersibles as pale, mushroom-shaped formations rising from the seafloor. These bacterial cities can persist for years, their populations cycling through boom and bust periods as nutrients become available and are depleted. The chemistry within these formations creates microenvironments so distinct from the surrounding sediment that they support their own specialized communities of microscopic grazers and predators. The pressure effects on bacterial metabolism in the deepest sediments create biochemical processes that operate at rates and through pathways unknown in surface environments. Some of these bacteria may represent the slowest living organisms on Earth, their cellular divisions occurring perhaps once every millennium while maintaining metabolic activity across geological timescales. These ancient bacterial lineages preserve biochemical capabilities that may represent evolutionary pathways from the earliest life on Earth. The magnetic bacteria that live in deep-sea sediments have evolved the ability to synthesize magnetic nanoparticles within their cells, creating internal compass systems that help them navigate the chemical gradients in their sediment environment. These magnetotactic bacteria can orient themselves along magnetic field lines, swimming up and down through the sediment layers to find optimal chemical conditions. Their magnetic particles, called magnetosomes, are so precisely engineered that they have inspired research into biological approaches to nanotechnology. The deep-sea coral gardens that grow in certain regions of the abyssal plains create complex three-dimensional habitats in environments where hard substrate is normally rare. These cold-water corals build their skeletons slowly over centuries, creating reef-like structures that support diverse communities of fish, crustaceans, and other invertebrates. Unlike their tropical relatives, These deep-sea corals derive no energy from symbiotic algae and must capture all their food from the sparse plankton that drifts past in the deep currents. And so, our journey through the abyss draws to a gentle close. We have drifted through realms where creatures paint the darkness with living light, where crushing pressures forge life into forms of impossible beauty, and where volcanic fires birth oases of abundance in the deepest cold. The deep ocean reminds us that life finds a way, always, transforming the most extreme challenges into opportunities for wonder. Rest now, knowing that far below, in the eternal night of the depths, these remarkable communities continue their ancient dance of survival and splendor.